Hello, welcome back. In the last video we talked about the structure of an atom. In particular we looked at this little thing, which is the nucleus. And in this video we're going to focus a little bit more on the nucleus. We're going to talk about the structure of the nucleus. We're going to talk about what makes a nucleus stable or unstable and what that means. So as you go through this, I think it may be useful to look at the periodic table. Currently this one link is my favorite link. It's a clickable, should be clickable in the video. It's an interactive periodic table that you can navigate through. And this will help you in going through problems and thinking about the concepts more deeply. So I encourage you to spend a little time with this. We're going to go over some of these very basic building blocks, and the better you understand this, the easier things will be later. Here we go. So I'm going to draw a cartoon of the nucleus here. I'm going to draw the protons in red. These are positively charged. I'll draw the neutrons in gray. This is a strange configuration when you think about it. You've got positively charged particles very, very close to each other. They have a strong Coulomb repulsion. What holds them together is a quantum force called the strong force, which I won't really talk about here. Each nucleus has an atomic number, Z, and an atomic mass, A. Z is the number of protons. So what I've drawn here is a helium nucleus with 2 protons and a total of 4 nucleons. That's protons plus neutrons. So every nucleus actually can be written like this. So if you have a nucleus element Y, it has Z protons and A number of protons plus neutrons. So I would like to talk now about what makes some nuclei stable and some nuclei unstable, with the ultimate goal of understanding radioactive decay. So a productive way to look at this is with this chart, which shows the stability of different nuclei. Here's a link that you should be able to click on in the video to navigate through this chart. On the bottom here, you're seeing the number of protons, Z, versus the number of neutrons on the y-axis. This line here shows you Z equals N, where there's equal number of protons and neutrons. And what you'll see here is that these nuclei in black are actually the stable ones. And what happens is, as you go to higher Z, stable elements become relatively neutron rich. So that's a first important point, which is that the ratio of neutrons to protons increases with Z. The obvious exception being hydrogen with no neutrons. But the other effect is that for almost every element with a Z greater than 83 is going to be unstable. So to understand this, it might help to run through a little sample calculation. So here is a carbon-12 nucleus. It has 6 protons, each with an atomic mass unit, AMU, of this value. That's just the weight of it. If you multiply those together, this is the number you get. Then it also has 6 neutrons, each with an AMU of this value. Remember that the neutron is slightly heavier than the proton. And so here's the mass of the neutrons. It also has electrons for electrical balance, much smaller mass, of course, as we learned last time. When you add all these components together, you get 12.099 AMU. Now, the carbon-12 atom, by definition, is 12 AMU. So therefore, there's some excess mass, or excess energy, and that's the binding energy of the nucleus. That's an important fact. The mass of the nucleus is always less than the rest mass of its components. Why is that? Because binding energy, it takes some energy to disassemble the nucleus. That energy is stored in the bound nucleus. So based on this, it's hopefully not entirely surprising that nuclei can decay into one another. And they do that because it's energetically favorable. You can see that with this graph here. What you're seeing is the binding energy on the y-axis versus the number of nucleons on the x-axis. And when an element decays, then it goes from a position here on the graph decaying down to another isotope here on the graph, and as a result of that, it releases energy. Energy is gained. So this process along this part of the graph is called fission. So fission is moving up along the curve of binding energy. An example of that will be the decay of uranium. So what you start with uranium, it's uranium-235 plus a neutron going to uranium-236. That's the activation. And then that radioactive uranium actually decays to barium-141, krypton-92, plus 3 neutrons, and some energy is released. Okay, so that was fission. Now the other way to get energy out is through fusion. In fusion, what happens is you climb up the curve of binding energy from a light element to a heavier element. That is fusing two light elements together to get a heavier element and release energy. So here's a classic example of a fusion reaction. This happens in the sun. What happens is you take a light element, which is deuterium. That's hydrogen with a neutron. You combine it with another deuterium element, and then those get fused into helium-3 plus a neutron plus some energy that's released. And that's what powers the sun. So in terms of the energetics then, elements can decay into one another. And now we're going to look a little bit closer at how that happens. And to understand that, we need to understand different isotopes of elements. So here we have, coming back to helium, this is the stable form, helium-4, but you can have different isotopes as well. So here, for example, we have helium-3. So helium-3 has the same number of protons, but instead of having 2 neutrons, it has 1 neutron. So we would write that as helium-3, 3 nucleons. So these elements are isotopes of each other. So in addition, we could have an element that has the same number of neutrons, but 1 less proton. The example here is a form of hydrogen, which we read as hydrogen-3. It's also known as tritium. So these two elements are called isotones, the same number of neutrons. All right, so if you followed along, you understand now quite a bit about the nucleus, how nuclei can fuse together or split apart, and how energy is released. What I did not tell you is what happens after that energy is released. What comes out, what particles, what other kinds of energy. And so that is going to be the focus of the next video on nuclear decay. I'm going to leave you with a little bit of extra reading in case you want to dig deeper, and I will see you in the next video.